I'm fine, sir.
How much does the car cost to repair? Any idea?
1,000.
So expensive. I thought just a minor. So the car can be drive, even though it was a bit damaged.
Yeah, I can drive.
Or can drive, and just drive it to the workshop. Okay. As long as you are, yeah, okay. Mistake does happen. Anything you want to clarify?
No.
Okay. So today we will do focus 24. If we got time, we do radioactivity. The question. Then tomorrow we will finish off with nuclear reaction. And then next week we do focus 25. And then we will start passive paper already. 19, 20, 21. If you can get that one done. Don't have much time already. Okay. So it's up to you to do and ask question. Okay, if no question to ask, let us carry on. Okay, these are, as I said, these are all the things that you need to remember for this topic. Okay. Right, number one, what is the answer?
Number 1.
Focus 24 in your book.
Number 1, donkey. Donkey, sir.
Why donkey?
Threshold frequency, I mean, it depends only on the frequency of radiation.
Intensity of radiation used in photoelectric emission is half the intensity. Which of the following is the new graph? Right? V is stopping potential, and F is the frequency of the electromagnetic radiation falling on the metal. So we are basically using this equation and then replacing the kinetic energy by EVS. Intensity does not affect the maximum kinetic energy of the emitted electron, and thus the stopping potential. So it's not in the equation. That means that intensity doesn't affect the stopping potential or kinetic energy. So you're right. Good. How about this one?
So go back, sir.
Intensity doesn't come in. Intensity affect the number only. Number of electrons emitted. Doesn't change the kinetic energy or the stopping potential.
Okay.
Okay. Light with constant intensity is incident on a photocell, which is connected to a direct current voltage source. Which of the following graph shows the variation with a current I to the photocell with voltage V of the source? Memory work only. Yep.
Donkey.
Donkey, okay, good. Number 3.
Donkey.
Donkey also. Light of frequency F is incident on the surface of metal. If the maximum kinetic energy of the emitted electron is K, H is Planck constant, what is the threshold frequency of the metal? Go back to the equation. No? That's the equation. Threshold frequency has to do with this one. Okay. So replace that one. W with HF naught. F naught is the threshold frequency. So HF naught. Take over there. Take K at the other side. Right? Take this one to the other side. Take KV the other side. That's why we got that. And divide by H. Okay. B. Any comment? Number 4.
C.
Cat, is it?
Wait, 1 minute, 1 minute. Boy.
Why? Let's see.
Boy.
A transmitting station emits light of wavelength lambda at a power P. Rate of emission of photon is given by, right? That's the equation. Power is energy or work done divided by time. And energy is given by the photon of energy HF as number. And we want rate N over T, HF down. Okay, donkey. Where did you go wrong?
You wrongly placed the value. I inverse it.
Carelessness, is it?
Yeah.
Okay, anything not clear?
Clear?
Number 5.
Wait, go back. So P over HF. Oh, the F become C over lambda. They switch it lah. That's it. Because I get
I
it.
just want N over T, so I take my HF down, cross multiply. That's why I get that. Then you want to replace.
Yeah, and then the F will become C over lambda, and then you make it lambda over
because
C.
C over lambda, yeah. C over lambda,
okay,
lambda
understood.
to the top.
Understood. Okay, can continue.
Experiments performed to show photoelectric emission. The frequency of light is kept constant while the intensity is increased. Which of the quantity below is increased?
Boy. Sure, boy.
Okay. Frequency is constant, intensity increase. Let's see. Physics involved. Basically, just using this formula. Is the number of photon. Is the energy of a photon. Is the area that the energy is falling on. That's the time. And E can replace with HF. Then your Kmax is energy of photon minus your work function. Maximum momentum of the which quantity will be increased. Momentum of the momentum is not affected because F is doesn't change, only intensity. So where F is constant, velocity of the emitted electron and momentum is constant. So false. About B. True. You increase your intensity, increase the number emitted. Maximum kinetic energy of the photon not affected. So false. Okay, because your F is constant, your maximum kinetic also is constant. Minimum de Broglie wavelength for the photon. False. Speed and thus momentum and de Broglie wavelength is constant, right? The speed is constant, doesn't change because it doesn't affect, right? It doesn't affect the maximum kinetic energy. So So intensity doesn't affect the velocity, so it doesn't affect the de Broglie wavelength. Okay. Good.
Okay.
Number 6. In the photoelectric effect, the energy of photon is used.
C.
Okay, let's see. To release the electron from the lattice only? No. Right? Photon release free electron. There's the work function there. So the energy is given to the to overcome the work function and then release as a release the free electron. As the kinetic energy of the electron, not only that, the force photon provide energy to both the electron and the work function of the metal. To release the electron from the lattice and the kinetic energy of the electron. Okay. So part of it is under the attractive force of the positive ions around there. So that is where your work function comes in. By the electron to produce a new electron called a photoelectron. So the D is false. The answer is C. Okay with that?
Okay.
Number 7. A semiconductor films become better electric conductor when illuminated with photon of energy greater than 1.2 electron volt. What is the corresponding maximum wavelength of the photon? This one is calculation. Can? Find the frequency first.
E equals to Hc over lambda. So lambda equals to 1.04 times 10 to the power -6.
Yeah. What's the answer?
Donkey.
Right. That is essentially the formula we use, Hc over lambda, and cross multiply. Put in your value for your H, that's your C, and then this is 1.2. Change it to joule times 1.6 and 10 to the power 19 at 1.04 micrometer. Donkey. Okay. We won't bother about this one. If we want to do all of them, let us try this one. Number 10. According to de Broglie, an electron of velocity v may behave like a wave of wavelength lambda. Which of the following graph shows the variation of lambda with v?
Donkey, they are inversely proportional.
Right? Put the formula.
Because lambda equals to H over P, P equals to MV.
And rewrite a formula in the form of cross multiply, take lambda up, take P down, P is MV. Then rewrite a constant one side. Okay, good. Donkey, good argument. How about this one? If lambda is the wavelength of particle with momentum P, which of the graph has a gradient equal to Planck's constant? Okay, same formula as before. Same formula as before.
Uh,
That formula, that's all.
A,
Nothing much.
A, A. The answer is A. The answer is A.
Are you sure?
Oh, no, 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 no. Cannot be, cannot be. Boy, boy, boy. The answer is boy.
That's right. Answer is boy. Good. Do you want to do all the question because we may not have the time?
Yeah.
Which statement is true of the Brody wavelength?
Donkey.
The wavelength of photon is independent of momentum. False. Wavelength and momentum are related. Wavelength of an object in motion is directly proportional to momentum. No. False. Inversely proportional. Velocity object is directly proportional to mass. False. Momentum is P equals mv. Greater the kinetic energy of electron, the shorter is the wavelength. True. Greater kinetic energy, greater speed. Right? Greater speed, thus greater momentum. Okay with that? Answer, Donkey.
Teacher, today like no half an hour, the break all right, just straight away 1 hour, right?
Depend on whether they allow us or not. No?
Okay.
No point in having a break lah, because it's the same topic.
No, don't want. Okay.
Electron can be considered as wave because they Yep. What's the answer?
Answer is boy.
Okay, good. Only wave can be diffracted. In X-ray tube, the characteristic line spectrum is produced when
C.
C, is it?
Yeah.
Let's look. An electron characteristic line spectrum is produced when an electron in the target atom undergoes transition from outer orbit to inner orbit. A, answer is A. When the electron, basically the emission line spectrum, that is what we want. So where the electron hits the inner electron, then the outer electron will come and fill the gap. Then X-ray is released. That's where we get the emission line spectrum. Okay. B cannot be. Kinetic energy of electron is converted into photon during deceleration. That one is a continuous spectrum. Mass of electron is converted into heat energy. No. Electron is knocked out from the target atom. This is the inner electron. In 1913, Neil Bohr suggested several postulates to explain the origin of the spectrum of hydrogen atom. Which of the following is not true of the suggestion? Energy of atom is discrete.
C.
Sorry?
C.
C, linear momentum orbiting electron may have any value. You're right, it's wrong. C is wrong. All the others are correct. We assume that linear momentum is quantized. Okay, what is the radius of the orbit corresponding to n equals to 4 of hydrogen atom? This one memory work, nothing can be done. If not, either you derive it, if you don't memorize it. Answer?
Boy.
Let's see. You derive, you can use this formula. Then momentum is quantized. Right? If you can remember formula, better. If not, derive it from these two equations and put in your value, n equals to 4. Okay, boy. 18. Which of the following statement is not true of Bohr's atomic model? Yep.
A.
Okay. Right? As long as it's in the permitted orbit or allowed orbit, then no radiation is emitted. B is true, C is true. Okay, you're right. Radiation is emitted when electron falls from higher to low energy level. How about this one? Yep. And
19. Donkey.
Donkey. Right? If you roughly can eliminate, this is visible light. See, visible light must be N2. So it could be right, B or donkey. It cannot be C or A or C. A or C will be this level, which is ultraviolet. So you have to calculate out. Lor. This is visible light and the shortest wavelength. Right? It's the shortest wavelength. So work it out. Your lambda is C, right? Cross multiply. Likely transitions from N5 to N2. Right? The other choice is from 4 to, right? This is the law, shortest wavelength. So you play with it, no shortcut. Make a guess, then calculate. You calculate correctly, then save time. You guess correctly, then save time. Right? That's your H. That's your C. Transition from N5 to N2. Right? Just take the largest value minus the smallest value. By right, it should be this one minus this one. Right? Same thing. Right? That's the value. And then this is the electron volt, convert it to joule. Okay, we are right. How about this one? Number 20.
Donkey.
Okay, let's count. 1, 2,
2,
3,
3,
4,
4,
5,
5,
6.
6.
Looks like you're right. Good. You won't bother about this one. You can try yourself. Let us try. Yeah. Okay, let's go to X-ray. X-ray tube emits X-ray of minimum wavelength lambda mean when the potential difference V is applied across the tube. If the graph of lambda mean against 1 over V is plotted, the gradient is, okay, what's the answer?
Boy.
Let us see. That's the formula that we use. The X-ray photon as work done, the cell relation to a potential difference. And we want lambda mean rearrange, take lambda mean across and EV down. Right? We want the constant to one side, lambda mean and then 1 over V. So that is your gradient. Compare with y equals to mx. Okay, good boy. How about 24? The penetrating power of X-ray, which is produced from X-ray tube, can be increased. Yep.
Boy.
Okay, let's see. Penetration depends on energy of X-ray. Increasing the current which flows through the cathode, that one increase the intensity and it falls, as this will increase the number of electron emitted. So it will affect the intensity of the X-ray. Okay, increasing the potential difference between the anode and cathode, you are right. True, increasing the potential difference increase the kinetic energy of the accelerated electron. So C will be wrong already. Focusing won't help. Right? This one you want to get rid of all the electron in all other direction except one particular direction. Using an anode made of an, right? That one doesn't come in, false. Okay, how about this one? The graph shows a spectrum produced by X-ray tube. If the accelerating voltage is raised,
A.
okay, I think you're right. Good. Using this equation, energy of the X-ray produced equals to the photon. You accelerate the electron to a potential difference. Then increase this one becomes smaller. These are all constant. Increasing the accelerating potential V will reduce the minimum wavelength. Okay, good. See any more that you want to do? Okay, we do one last one. After that, we go to structure. This one. You can try the rest. If you want, you can ask me tomorrow if you've got problem. In the X-ray tube, the minimum wavelength is 4 times 10 to the power minus 11 meter. If the potential difference between the cathode and anode is decreased to half the original value, the minimum wavelength becomes can use the correct formula. We have been using the formula all the while. Play with the formula, that's all. That formula. Take all the variable to one side. H, C, and E are constant. You can calculate it out, like calculate V1. You can calculate your V first. Unnecessary work lah. After that, half the V and then calculate again. No? Can or not? Easiest way is to take the variable to one side, lambda mean and V, E take it down, constant to one side, and then inverse proportion. So argue it out. Potential is half, inverse proportion, this is half. This one must increase, must be double. See? Can?
Okay.
Okay, let's go to structure question.
Question B.
Oh, let's try one last one, Brett's formula. Make sure you know how to do this one. Diffraction of X-ray in crystal is shown in the diagram below. The maximum diffraction occur only when angle alpha, that one angle alpha, between the incident ray and the reflected ray, right? That's angle alpha, is between 50 and 80, 180, 108, sorry, 50 to 108. What are the possible value of lambda of the X-ray and interatomic distance of the crystal? Yep, Ken? Go to the formula, Brett's equation. Right, and theta is half of alpha. So if that's your value, it will be 25 and 105.54. And you want lambda over d, take the d down. So you got sine theta. And put your value of theta inside this equation. That's what you get. Right? These two range. So these are the range that you have. Then you can calculate your lambda over d. Lambda over d, 0.6, 1.8, 1.2. The answer is C. C is the one that's only within the range. No point wasting your time on that. You can try that. Okay or not? This is more than one now. Okay, if no comment, let's carry on. Number one, let's try number one. Work function for cesium is 2.14 electron volt. Calculate the maximum kinetic energy of the photoelectron emitted from cesium surface when illuminated by light of wavelength 2565 nanometer. Can? What's the answer? What formula to use? Yeah, the work function. Convert it to joule. Then photoelectric emission equation. Right? That's your H.
Yeah, and then you
That's your
minus
C.
the 2.14 thing here.
That's the energy of the photon. Right? Calculate energy of this photon. And use Einstein's equation. That's the energy. That's one function. It's energy. One function. You get 1.0 10 to the power minus 20 joule. You want to convert it, you can convert it. Okay. Anything not clear?
Okay.
Okay, let's try number 2 and 3. In photoelectric experiment, light of wavelength 450 nanometer is incident on the metallic surface with work function. Same as before. Determine the velocity of the most energetic electron emitted from the surface. Calculate the stopping potential. What formula to use? Can or not? Yeah, convert your work function to joule. First step. Then calculate the energy of the photon. That one. That's your H. That's your C. That one, change it to meter. In joule. And use your Einstein's equation. Photoelectric emission equation. Right? That's your HF. This is your W. Put in your value. Calculate out. And after that, use your kinetic energy formula. Okay, take a 2 up, take the M down, cross multiply, then take the square root. Put your value of kinetic energy inside there. And calculate out. How to calculate the stopping potential? How to calculate the stopping potential? Any idea?
Yeah,
What formula to use?
EV equals to 1/2 mv square.
Don't need to go that far lah. Just use this one equals to EK max good enough already. EV equals to half mv square. Right? Take that as K because you already got K there already. Divide by E, that's all. So that's your K value. Right? That's your E value. Then we calculate. Okay. Anything that you need to explain further?
No.
Okay. Let's see which one we want to do now. Let's try number 3 and then after that number 5. Light beam of wavelength 0.11 nanometer collide with an atom. After the collision, an electron is emitted with kinetic energy 180 electron volt. Calculate the energy absorbed by the atom. Yep. What formula to use? Same as before.
Hc over lambda minus the
Right?
kinetic
Use
energy of the
this
electron.
formula to calculate the energy of the photon. Put your value inside as your H, as your C. That one convert it to meter. So that's the energy of your photon. Right? So this energy that is absorbed. Then how to calculate? How to calculate the velocity of the electron emitted?
Uh, 1/2 mv square equals to the
Right? To convert your kinetic energy first to Joule. Right? Energy absorbed equals energy of photon minus kinetic energy of the emitted electron. Okay. Can or not? Anything not clear? Here's your energy converted to that one there. That one we use it here. Energy absorbed, remember energy of photon minus kinetic energy, this one. Have to convert everything to Joule or use everything in electron volt. So you can write your answer in Joule or electron volt. It's your choice. Yep. Anything not clear? Okay, okay, let's go to number
okay.
5. Need more time? Need more time to digest? Oh, yeah, all right.
Yeah, give me 1 minute.
Okay.
Yeah, okay, teacher.
So basically, this one is just telling you the energy of the photon contribute to kinetic of the electron, and the other part is absorbed by the material or by the atom. Okay. You can try number 4 if you want, and then let's try number 5. We jump because we don't have the time to do everyone. Electrons are accelerated from rest to a potential difference of 1,500 volt in vacuum. Many electrons are found to emerge from a very thin crystal with a deflection of 2 degrees. When the accelerating potential is half, calculate the ratio of new electron speed to the initial speed. Yeah, this one is just playing with formula. What formula to use? Right, that's all. You accelerate electron, That's the energy of the electron. And that becomes the kinetic energy of the electron. That's the work done. Okay, QV. Then, since you want ratio, take all the constant to one side. You don't want half, you don't want your mass of electron or charge of electron. So you want a ratio of velocity, take your capital V down. That's the equation. Right? EM and take all the constant to one side. 2 is also a constant. Then rewrite. Right? That's the new one. Equation. That's the old one. Then take this one down. Take this one up. And square root, you get this equation and put in your value. Okay. Anything not clear? Yep. Talk to me. What is not clear?
Yeah, okay.
Right. Next part, you want to calculate the new wavelength. So we are just using the same formula. Right. That one there. Where there's your V, is that one. And calculate your speed. Right. Can have different way of doing things. I'm doing it differently. And calculate the velocity first, because I want to find a de Broglie wavelength. So that's the speed. Right. That's where we calculate. Then the de Broglie wavelength is your Planck's constant divided by momentum. I can use as what we have done that. Take all the constant out if you want to. Right? Just putting your that equation into here if you want to. And take all the unknown out. I can calculate one by one, step by step. Calculate the speed first. And put there's a mass, there's a speed there. And calculate your lambda. There's the O wavelength. Sorry, I calculate a new wavelength, I calculate a new speed. Because that is your half of that is this one. So that's a new speed there. Then there's your momentum, mass times velocity. And new angle of deflection, use Bragg's equation. 2d sine theta equals to n lambda. Okay. Sine theta over lambda. I'm basically using what's happening? Sorry, I think I did just adjusted this morning and yet number 2. Okay. Okay. As I said, you can always replace this one. If you don't want to calculate this step, you can replace that's your momentum is mass, velocity, that's the equation for velocity. And then that m and that n can cancel off. You still got m up there. That's what we did. That's the equation. Right? If you want, you can use that equation to calculate out. Same answer. Then Bragg's equation. Right? As I say, you can calculate as what we did before this one. If not, take all we are interested in new wavelength and new angle. New wavelength and new angle. And the others are constant. D is constant, N is constant. Sin theta, lambda. Lambda is just that. That's what we are doing here. So this one becomes the top there. Remove all the constant as before. Okay, this one becomes on top there. So constant, to want all the constant, unnecessary calculation. So I want this one, that's theta. And 2, E and M and H are constant. I just want root M, root V. Right? So that's a new one. That's the old one. And then I want the new value, this one. Take this one down. Okay, so this one is V2 is 750. What happened? Oh, that's 2 degrees. Then calculate. Oh. Can or not? Anything not clear? Talk to me. Anything not clear? Ask me to explain. Which part you are stuck?
So the C, right, teacher? How come it became square root V2
Which
sine
one are you
theta
talking
2?
about? Part C, yeah.
Part C.
Okay, which one are you talking? Which part are you talking about?
The sine theta and then times square root 2 EVM over
Okay,
H. How come
this
that one?
equation is it?
Yeah, how come that one constant?
The 2 is constant. 2 is constant. E is constant. M is constant. So we can take them to the other side if you want to.
So
I didn't show
V
the
is not
step.
constant.
I take all the constant H to the other side. I only left with sine theta over root V. Take all the constant to one side. Easier. Rather than put value in an unnecessary calculation.
Okay,
So the only variable
understood.
is theta and V, that's all. Theta and V, that's your V, that's your theta. Can. Okay, let's do one long question. You can try the rest. Yeah, why I didn't remove that? Well, can try it out first. After that, I'll ask you a question. Let me remove. Oh, I don't know why I didn't remove it. Something is wrong with my computer. Somebody is changing my thing. Thought I've done all that. Okay, let's try on essay question. Define stopping potential in photoelectric effect. Okay, this memory work. Yep. Can. Can or not, can or not. Right? Is the reverse potential or negative potential different required to stop all the electron from reaching the anode? Okay. State foremost important result for photoelectric effect experiment. Okay. Can remember? There are 5 of them. You are required to write down 4 only. Can or not? Any idea? Your book is a bit confusing now.
Okay.
Cannot. The incident electromagnetic radiation falling on the metal surface must have a minimum or threshold frequency for emission to occur. Number of electrons emitted increases with intensity. Maximum kinetic energy of emitted electron depend on frequency of the incident radiation and not on intensity. Emission is instantaneous. That's all. Okay.
Okay.
Work function is given 2.14 electron volt. Calculate the maximum wavelength of light that ejects electron from cesium target. Okay, what should I do? Tell me the step. You must do your homework. If not, you are going to lose out. You lose everything. Forget what I teach you.
Lambda equals to HC over W.
Right, convert your work function first. Basically, we want to calculate your kinetic energy. Right, work function. Right, in terms of energy, HC over lambda naught. So lambda naught, calculate out HC over W. Put in your value for H as your C. As your that one there. So you get that's your wavelength. Threshold wavelength. Right? Threshold wavelength is the maximum wavelength now. And if the light of intensity, this one is limited on cesium, calculate the maximum kinetic of the photoelectron. Okay, same thing. Put in your value of H, this energy of photon, and there's your C, that's your wavelength. Calculate out step by step, or you can use a formula straight away. Right? That's the formula. EK max is HF minus W. Right? This is your HF. You calculated that. This is Joule. W is that. Okay. You can leave your answer as either Joule or electron volt. Any comment? Anything not clear that I need to explain further?
No, not really.
Okay. See, usually they will try to cover all the syllabus, the long question. Not concentrate on one topic only, one subsection only. If this page of question paper is limited by 120 watt per meter square of light with wavelength 55 nanometer, calculate the power received by an area of 1.0 cm squared. What should I do? Remember, this is your power. This is your wavelength. Sorry, This is your intensity, not power. My carelessness. Intensity. Yep. What formula should I use? That formula? Right? Power equals to intensity times area. Power is given. Sorry, intensity is given. This is your intensity. Area 1 cm converted to meter square. Get your answer. Number of photons striking each square area, each square cm per second. What should I do? Any idea? Right? Power equals to number with a particular energy hitting the surface and then divide by time. Right? Total energy divided by time. So you want N divided by T. Right? Can replace by E equals HC over lambda. Okay, you want NT, take lambda up, take HC down. That's what we get. Put in your value. Right? Power. What is that? Lambda. I want that. Change it to meter. There's your H. There's your C. Okay. Anything not clear? Anything that you want me to explain further?
No.
Okay, let's go to checkpoint then. Ready activity. Do some question on that before we call it a day. If not, we don't have much time left. Tomorrow we'll finish the last one, nuclear reaction. Okay, 25.3. Yeah. Okay. How to solve this question? A radioactive sample of mass M emits 6.3 times 10 to the power 7 alpha particle per second. What is the decay constant of the sample? Right? Usually your first term work you need to remember that's the number of mole. Right? Number divided by Avogadro's number or mass of the sample divided by your relative molecular mass. Yep. How do I do that? Right? Remember this activity. There is no half-life given. So you have to use your A equals to N lambda. Right? So to find A is given, this is your activity A. Right? You have to convert that to a number of atoms. Okay, using this formula. Right? And calculate that. So Na take across there. Right? That's your Na. That's your mass. That. And then that one is change it to kilogram. Okay, that's your MR. Okay, out. A equals to N lambda. Okay, your lambda. Take your N down. Right? That's your N. Okay, Ken, anything not clear?
Okay.
Need more time to copy?
No.
Okay, let's go to number 2 then.
So the video you'll send right later.
Yeah. I always send it the same day. That's why I never forget. Right? There's a discipline that I have to do. Record everything down, send it before I do anything else. Isotope radium 226 has a half-life of 1620 years and decay to radium 222. How long does it take for 80% of the sample of radium to decay to radon? Sorry, radium 226 to decay to radium 222. Right? How to interpret the 80%? Can what should I do? Fraction remaining. There's a fraction remaining. Right? 80% has decayed. So fraction remaining is 20%. No? 20% is 0.2. Right? There's number remaining. That's the original number. And this is equal to 1 over 2 to the power n. Right? So you take the log. Right? I simplify the step. Basically, the next step should be take the 2n across there. Take the 0.2 down. So I log 0.2. Can you understand? If not, I will redo it for you. Can or not? Can or not? Can or not?
Can.
You either do it this way. Right? If you don't want, you can use the exponential way. Same thing. Right? Fraction remaining still the same thing. Then calculate your lambda. Ln 2 over half-life. Calculate that one per year. And fraction remaining is 0.2 equals to E minus lambda T. Okay, you take anti-log. Right? You get minus lambda T. Sorry, what have I done? I simplify the step too fast. Yeah, correct. Can see, if cannot, I show you the step.
Show me the step, Joe.
Okay. Right, from here, I take the ln. Ln 0.2. Yeah, what's happening? Okay, that's the step that's missing. Okay, that's 0.2 here. Right, I take the n naught down. That's why I get this one. Then I take the anti-log. Right? Log this one. So this one becomes minus lambda t. Then I want t, take my minus lambda down. That's what I get. And put in your value, lambda. That's your lambda. I use per year, so my answer will be year. Okay. If okay, let's do one last one. Anything not clear?
Yeah.
Okay. Activity of a sample of polonium, half-life given. What is the decay constant? How to calculate? Yep. How to calculate the decay constant? Memory work only, nothing much. Yeah, same formula that we use, this formula. Decay constant, log 2 over T half. You are given T half. Put your value inside there. You use day, then it's per day. Calculate the number of polonium-210 atoms in the sample. Yeah, what formula to use? Got activity. So start with activity. Right? You have to convert to per second since we need it for part B. Right? Activity is n times your lambda. Right? You have to calculate n. You calculate n. That's your lambda. A is given. That's your A. Right? Put in your value A. That's your lambda. Calculate terms. How long does it take for the activity to decrease to 50? Yep. What formula to use? Yeah, that formula. Or you can use A equals to A naught 1 over 2 to the power n if you want to prefer that method. Or use the standard one, that one. Then put in your value. Right? A over A naught. Right? This is A. This is A naught. Right? That's your A naught. That's your A. That's your A. Right? Lambda. Lambda is that. T. Take your anti-log. Get your answer. Either in second or in day. How many atoms of polonium-210 remain in the sample when the activity is 50? Okay, we calculate, use the same formula there. That's all. You know the activity, right? N equals to A over lambda. Activity is 50. 50 lambda. Right? That one cannot use per day. Have to use cannot use this one. Use per second. Okay, we will stop here. Anything that not clear, you can try the rest yourself. Let me see whether I should try any more question. Okay, I think we will leave it for tomorrow. Yep. Anything not clear? You can try the rest.
Clear.
Don't know, you can ask me. I will stop here. I think you are too tired to go any further. Anything? Anything not clear? Anything you want me to explain further? You can try 25.4 tonight.
Okay lah.
If you have the time, try 25.4.
Okay.
If not, we'll call it a day.
Record date, chef. Okay. Okay, thank you.
Okay, bye-bye.
Bye bye. Have a good day, chef. Bye.
Okay.